Hi everybody, sorry I had some problem with the streaming server, but now everything is fine. So I introduce you Elena Moretti. She's a colleague working in very high energy now, and even if she looks like she's 18, she finished her PhD some years ago, and the topic of her PhD was GRB, gamma ray bursts in high energy with Fermi instrument and with the Agile instrument. And then after that she kept working on this topic in Stockholm and even later in MPI Institute for Physics, where she's working right now. So GRBs are very important for her. She's studying GRBs not only in high energy, but also in very high energy with MAGIC instrument. She also worked a bit in X-rays, so she has an overview not only of high energies, but also of X-rays. And this, of course, is useful if one wants to have an open mind on what's happening out of there with these violent events of gamma ray bursts. So thank you to be here, Elena. And okay, we can't wait to hear from you.
Thanks. Good morning, first of all. Thank you for introducing me and thank you for the invitation. I will start with the topic of high energy and very high energy. And first I will introduce GRBs. Maybe some of you know already this. If I am boring you, please tell me so, and we skip the introduction. So with high energy, I mean everything that is ongoing above 100 MeV, and with very high energy, I mean everything that is ongoing. It's not working anymore. Ongoing above 30 GeV. I think. Okay, so GRBs first, as I said. GRBs are quite strange phenomena. They are serendipitous, so we don't know when they happen, and they occur in a random position in the sky, more or less one per day. Sorry, Marina, is this not working? No, mostly I cannot point. As I said, they are distributed isotropically in the sky, so they probably have cosmological origin, and then, but it's discharging. Lucy? Okay. And as now we can measure also the redshift. We see that they come from quite distant. The most distant one is about Z9. The flux you can see here is about 10 to the minus 7 to 10 to the minus 4 ergs per centimeter square per second. And most of their energy emitted is in the MeV range. So we normally classify them in several different ways. First of all, they have two phases that are normally that are present. The first phase is called prompt phase, and the second phase is called afterglow phase. The prompt phase is this one that can last from seconds to maximum around 1,000 seconds. The afterglow phase, you can see here, it lasts for very long. This is 10 to the 5 seconds after the explosion, after it starts. So very long. This is days, more or less, and then it faints, and we cannot see anything else from it any longer. Then we categorized them in two ways according to the duration of the prompt phase. So according to this part here. If it lasts for less than 2 seconds, then it's called short. If it lasts for more than 2 seconds, it's called long. In both cases, the afterglow phase is there. They have quite different light curves. Here is a collection from Batze. You can see that it can be just one single peak as on top right, and it fades away, or it can be several peaks and so on. What is clear is that they have quite high or very fast variability, some of them around 10 milliseconds. So what is happening in the central engine, it changes very quickly. And this is what is reflected in the light curve. Now we go back to the progenitor. So what kind of sources emit gamma ray bursts, or what could be? For now, a final answer we don't have. We are sure of this. But there are a couple of possibilities that we normally look at. One is the coalescence of a massive system, of binary massive system, and this is normally thought to be the progenitor of the short gamma ray burst, and the other is the death of a massive star, and this is what is thought to be the progenitor of the long gamma ray burst. Indeed, some of them have been connected to supernova. So no matter what is the progenitor, what is happening, at least for the standard model, what we call the standard model, is that the gravitational potential energy that is in this kind of systems, it gets transformed into kinetic energy, and so a fireball, what is called a fireball, is emitted, and now we look at this cartoon down here. So you have the central engine, the inner engine, that no matter what it is, then it emits blobs of plasma, and these blobs of plasma propagate. And because the blobs of plasma are emitted with different Lorentz factors, then sometimes they crash into each other. And this create internal shocks, which are here, and then external shock with the medium outside the system. The internal shocks are thought to be the reason of the prompt emission, while external shocks are thought to be the reason for the afterglow phase. Okay? Just because it's super sexy now, of course. In the case of short gamma ray bursts, so the coalescence of massive, of compact objects, this could be a connection with gravitational waves. I'm sure you've been you heard of the detection of gravitational waves, but also the possible connection of a signal in electromagnetic. We're not going to cover that, but that is a possibility. So the strange thing up to now is that no matter how is the light curve, what is kind of light curve, and no matter if it is short or long, the spectrum is quite similar to each other. So there is a very wide spectrum that it covers several quite a wide energy band, and it seems to be non-thermal. The paradigm up to now was to fit it with a band function. Band function is just a formal function. It's just two power laws smoothly joined together to describe this rising and this falling part. Okay, and up to now it worked very well. Indeed, was the function to compare GRBs with. But now we will see later on that is not longer the case. So this spectrum is thought to be non-thermal because of the wide coverage. But now we'll see there are two line of thoughts to explain this kind of spectrum. One is exactly non-thermal, and the other instead is thermal. So for the non-thermal part, the idea is that inside this, in the internal shocks, what happens is a synchrotron emission, actually, from a population of electrons. So here you have your population of electrons, say with a spectrum of -2, and at a certain point, the population of electrons is cooled down, and it has a break. And so from, this population of electron, the synchrotron emit, and then you come to this part here, which is the gamma spectrum, that has a rising part that is thought to be about -3 halves. and then a falling part. And this is very similar to what I told you before of the band function that has two power laws that are smoothly joined together. Okay, and the peak would be, the peak of the distribution would be exactly the maximum acceleration that the electron can have before cooling. The other competitor of theory to explain this spectrum, the GRB prompt spectrum, it's thermal. So I know that this sounds a bit crazy because thermal gives you very, very narrow spectra, but there are ways of enlarging this spectrum, both from a geometrical point of view, so the way you see the jet enlarges your distribution, and also it can happen that before the photosphere, so before the thermal energy is released, there are dissipations. Okay, so below the photosphere there are dissipations. This modifies your thermal spectrum before it's released, and therefore it widens it. So this is the picture before we go into the detections that Fermi-LAT and MAGIC, well, Fermi-LAT does and MAGIC, we hope. Thank you, Peppa. And this is just a connection, I think, between my field and your field. So this is probably mostly your field, I think. And over here is mostly my field. We have quite a wide energy that separates. Of course, optical can be looked from ground and from sky, from the space. For the gamma, around the MeV range, up to few GeV, we observe it only in orbit, because the gammas cannot penetrate all the atmosphere to be seen on ground, and therefore we use satellites. While here is missing, more than this, the gamma will not penetrate, but we can still look at the products, so to say, of this gamma in the atmosphere, and we look at very high energy. So at greater than 30, more or less, GeV, we can look at these gammas from ground with Cherenkov telescopes. So the first instrument is this one, that is the satellite. It's called Fermi, and it has inside two major instruments. One is called LAT, and it's here on top, and the other is called GBM, and it's around the spacecraft. The GBM stands for Gamma Ray Burst Monitor, so it's dedicated fully to gamma ray bursts. And this kind of detectors are scintillators, and they are made to cover this energy range, so from 8 keV to 40 MeV. While the LAT here, it's a different instrument that we are going to see now, and it's made to cover from 30 MeV through to about 300 GeV. And what you can see from here, LAT is actually, well, the spacecraft is not so big. LAT is actually more or less this size, so it's not a big thing. Okay, let's look at how LAT works, because you can imagine that detecting gamma rays at this energy is quite difficult. You cannot lose length, you cannot use mirrors. You need for the gamma to interact as a particle. And so the particle, which is the gamma, is then converted, okay, into a pair of electron and positron. Because of the massive, because there is a presence of massive nuclei, so in this case it's layers of tungsten here, the gamma can pair produce. And then once we have this pair of electrons, we can see them while we can track them with a tracker. That basically it's an instrument that tell us their position, and then collect their energy with a calorimeter. So, sorry. what we can do with the tracker, we take these tracks that we see, and then we reconstruct vertex, and from the vertex we can see where the gamma was coming from, okay? And this is how LAT works. Okay, well, LAT is modular, and it has all around it some anti-coincidence detector to reject particles that are in the sky, which is most of the background. So charged particles would look like gammas, but we reject them. So let's move to the GRBs that LAT has seen, and Fermi actually in general. This is a picture, or actually a map of where the GRBs from the GBM detected happen. And as you see, it's very, very isotropic, as I said before. Sorry. And now GBM has more than 1,000 GRBs. This was quite some time ago. I think we are about 2,000, so it's quite a large collection. And we start to have also some study of the general characteristics. And so what it results from this general characteristics is that the spectrum is not longer, the band function is no longer preferred to fit the spectrum. So as you can see here, the percentage is quite low. About 15% of the spectra are fitted with the band function. Most of them are fitted with a Comptonized model. So it seems that these GRBs have a cutoff in the spectrum. Of course, this is an improvement because before we could not see, with the instruments we had before, we could not see this wide range of energy, and therefore we could see only partial. But now that we extend our energy range, we can see better in their spectrum. And it seems that these GRBs have no just a band function, but also an extra component. Here we can say an extra bump that is thermal. And we can see this both in the time integrated spectrum. So this is what we normally do. You can collect all the photons that come in the prompt phase, and you can look at the spectral characteristics. Or what you can do is try to slice it in small slices to look inside of, basically to look at the time scale of the variability, and look what happens to the spectra and how they evolve. So this is an integrated one, and we see this kind of deviation, but also in slices, very, very thin slices, like this one. You see here what is the slice that is that here you have the spectrum of, and you can see the presence of an extra bump in the spectrum, and this bump could be actually thermal. So about what I said before of the two competing way of interpreting the spectrum, it might be that actually what we see is not one or the other, but it could be that it's joined. So there is a thermal part, and there is also a non-thermal part. So the non-thermal part would be this wide part here, and then on top we could see just the thermal. Sorry. But actually in one case, we saw a very, very narrow distribution. As you can see, this GRB, which is quite famous for LAT members, it shows a very, very narrow distribution, both in the integrated spectrum and in the time resolved. This is one slice in the time resolved spectrum. So this burst shows that it's possible to have thermal emission. And furthermore, now you don't see it here, it seems that in the first phase of this of the prompt emission, it had very, very narrow spectrum. And then in the second phase, it widened. So it's possible that the thermal emission, it gets somehow afterwards dissipated internally, and so the spectrum can actually be widened, although it's a thermal spectrum. And this is actually the first kind of mark proof that there are thermal emission even for this high energy emission. So as you can see already here, there is an extra component on this spectrum that is a bit puzzling. It starts at very low energy and it goes along. Now you don't see because this is a time resolved, so it doesn't have much statistics. But it goes on until very high energy. And this is what actually LAT sees. So up to now, we looked at what happens in the GBM part, so up to, say, 40 MeV. And now we look at higher energy. And what we see is that in some bursts, during the prompt phase, we have an extra power law. Here you see the time-integrated spectrum. So you see that there is a power law that starts at very low energy and it goes on up to very high energy. And this is a quite intriguing fact because it seems that there is more energy that is pumped from the central engine and we don't know where it stops. So there are a few cases, for example, this is again the GRB that I showed you before, that there is this main peak and then there is an extra component. In one case only, we saw the cutoff of this extra component. And this is this GRB. And this tells us that most probably at a certain point this power law will be cut in energy and we will not see it at very, very high energy. But let's see later what we saw in other GRBs. So to summarize the part of the spectral point of view, as I said, we have that before the launch of Fermi, there was this paradigm, which was the band function, and now it's not longer valuable. It's not longer the paradigm. As you can see here, these are the first catalog of LAT-detected GRBs, and the first one influence are fitted by something different than just the band function. And as you can see, the last one influence, so the ones that we have less photons, we go back to the band function. So most probably this was actually just a way to summarize the spectrum because we could not see it better. So let's move on to the time part. I'll try to be quick on this. A few more things that happen that's been discovered from LAT is that the emission that has higher energy, it starts later. You can see here a couple of examples. This is a short burst and this is a long burst. So at the MEV, you can see that it starts now here and there is nothing at very high energy. So, at high energy. At the high energy, everything starts later, and it seems to be delayed as higher the energy, as the more is delayed. Not only that, but the component that we see at high energy, it seems to be also emitting for much longer. And here you can see that when the burst at MEV is, the prompt phase is done, we still see emission at GeV, in the GeV range. And here you can see more or less it goes on for about 10 to the 3 or 10 to the 4 seconds, the emission we see. So it seems that when we look at the full picture, the prompt phase that we see in the GBM is a bit different from what we see, the component that we see in the LAT energy range, so at GeV. And this one is short and very variable, while this one, it's long and quite stable. As you can see here, this is what is being detected from LAT, and it's very similar to the decay that the normal afterglow in X-ray presents. So it's a shallow decay, more or less it goes to time to the -1. But let's try to move on to what happens to higher energy. So now, up to now, we saw quite a full picture from what LAT sees, But we want to see further, because we learned that the more we look at them, the more we learn. And there are possibilities, at least few, to catch these GRBs with the Cherenkov detector on ground. So there are, here you see two possibilities of photons, of the highest energy photon that is being emitted from these GRBs in GeV. So about 30 GeV has been emitted from these GRBs. In times, well, here it's very quick, but this is 80 seconds after. So these GRBs are possible to be caught with these Cherenkov telescopes. And even more, one extraordinary example we had in the past, this GRB that was quite close, 0.34, which is very close for GRB people. It was very, very, very bright, and it had a photon, actually a couple of photons of about 100 GeV, which is quite high energy. And this guy could have been caught by the Cherenkov telescopes on ground. Actually, the LAT emission went on for 20 hours, so LAT could see for 20 hours. This kind of very high energy photons start to question the general picture of the afterglow. So now I did not focus on the afterglow emission phase, but most probably it's synchrotron, at least up to now, because it's been seen both in X-ray and optical, and sometimes in radio. The general picture is that it is synchrotron emission. But with these very high energy photons, so about 100 GeV, you start to question the possibility that the forward shot with the medium can emit this high energy. Okay, so if we can see them with the ground-based telescopes, with Cherenkov, we can have more information on this side, so on this long-lived part, which is most probably afterglow. Yes, so let's move now into Cherenkov astronomy. Just to be quick, Cherenkov astronomy is done on ground, as I said at the beginning. But what we use is to have our atmosphere as the calorimeter, okay? So the gamma comes in, as you can see here, comes in, and then instead of using like the layers of tungsten for like what is done in LAT, we use the air. And at a certain point, the gamma converts into two photons, a pair of electrons, two electrons, and then from that it cascades into more and more and more. And what we see is then the products of this cascade, or better, the light that is emitted by this cascade. The same can be done from hadrons. So here you see a hadron that interacts with the nuclei, and then it cascades. And so the major part of the background from Cherenkov telescopes is hadrons that produce very similar signal or showers in the atmosphere. Now we have a video, but I think it doesn't work. Let me try it. If it not, yeah, it doesn't. 2 seconds. Okay, wait. So, as I said, it's not full. Oh. As I said, once the gamma enters and starts to generate the shower, then the shower is has charged particles that travel into a medium, which is the air. And when this happens, and the velocity is proximal to the light velocity, then the particles generate, the charged particles generate a light that is called Cherenkov light. That is what normally is seen also in the nuclei of nuclear power plants, and it's around bluish. So this video is actually what happens if you, let's see, Yes. Here you see the gamma that enters and then it creates the shower. And then the shower propagates into the atmosphere. And then it starts to shine a light that is a blue light. Then it continues on. So it transmits to lower part of the atmosphere where we actually have our Cherenkov telescope. Then the mirror reflects the Cherenkov light and it sends into the camera. So this part here is, well, the last part is very similar to the optical part. So we actually look into light, but we try to look at what has been has generated this light. So the shower that has generated this light. This is more or less how Cherenkov telescope works. So then, as I said, you have the gamma incoming gamma, and then you have the cone where this Cherenkov light is spread. And what you gain here is a quite big effective area with respect to Fermi lat. You know, Fermi lat, as I said, is something like this size, and it means that it can collect a little amount of photons, while here what you gain is in effective area. So even if the signal is very small at this energy, you can have more collection area, which is important. And also, when you look at the gamma with an array of this Cherenkov telescope, you can have a stereoscopical vision, so you can better confine where it comes from. Like when you look up and you look at the rain with your eyes, you can see, you mostly can track where the rain is coming from. And the same does do the Cherenkov array. So what I'm working on is are two kind of Cherenkov telescopes, or Cherenkov experiment. One is called MAGIC and the other is called CTA LST. These two, well, I'm sure maybe you've seen it if you've been to La Palma, the observatory there. They are 217 meters telescopes, and their energy range starts from more or less 50 GeV, more or less. They have been made in the carbon structure to be fast repointed for GRBs. So they can repoint to a GRB in any position into more or less 30 seconds. From 30 to 40 seconds. So it means that we have the chance with them to catch the prompt phase. So what has been done so far? I'm telling you already, there is no detection. This is unfortunate, but we are checking them. We are constantly follow them up. And here you see the delay from the prompt emission, well, from the alert to when MAGIC has been started its observation with respect to the zenith angle. And as you can see, we are following them in quite a large part. Most importantly, we are trying to start to follow them from less than 100 seconds. So more and more in the years, the procedure for following these alerts has been perfected. And now we are normally looking at them in few seconds after we receive the alert. We follow up about 10 GRB per year, more or less. Most of them are triggers from SWIFT. I don't know if you know, this is an X-ray instrument that is dedicated to the GRB. And it has a very good localization for the GRB, while the GBM, the instrument I was talking before, does not have very good localization, so we have difficulties to follow because their error is typically of the order of 3 degrees in the sky, which means a big chunk of the sky to follow, and we normally don't manage to go that far. So we normally follow them up to a zenith of, down to a zenith of 60, so quite a wide range. But we have some filters, as I said, for the localization precision. So we cannot follow, for example, all the alerts from the GBM, although we would like to. Some examples on how well we can follow them now. This is the delay. And so some of them we caught or still in the prompt phase, you see. But this is, of course, serendipitous, and we try all the time our best. You can see here, most of them we follow around between 40 and 50 degrees, which is normal. And some of them we caught with the reasonable zenith, like this one as well. You see, zenith to have good chances to detect them, because, you know, very high energy gammas are cut off by EBL absorption, extragalactic background light, and so if they are exploding but they are too far, the chance is low to detect them with very high energy. So some of them, of course, we have possibilities like this one and this one, but for now yet not. We have, of course, tested some models. These are actually all upper limits, but also from LAT point of view. And we try to look inside the synchrotron emission for the afterglow phase. Of course, now we have still upper limits, and so not yet constraining. We'll see with more GRBs to come. And we are studying it more and more. What is the next phase after MAGIC is CTA, and in particular LST. Why in particular LST? Because LST has the same philosophy, so to be fast in repointing light, light structure to fast repoint, and it has a very low energy threshold, so about from 20 MeV, 20 GeV, which means that the photons we've seen with LAT can actually be seen with LST. As you know, the north site, which is La Palma, is the prototype is in construction, and we hope to be operational in 1 year. Let's hope so. Well, at least to finish, start the commissioning and so on. This is a bit of a prediction for LST. I'll go quickly over this. So the detection rate is thought to be 0.5 per year. I know it's very little, but it's still very good for Cherenkov, because you have to think that the satellite have a duty cycle of more or less 100%. You can always look at the sky, but as you probably know, when you look at the sky from ground, you can look at them only in nighttime if you look at optical photons, which means that your duty cycle is already less than half. And then there is bad weather, and then there is that these things happen all over the sky, so half of the sky is not reachable to you, and then there is the fact that the localization is bad. So all these factors sum up to having more or less 0.5 for LST, 0.5 hope of detection per year. We'll see. So to summarize, and here I conclude, in the lower energy range, so between MeV and few GeV, we see that the band model is no longer the paradigm for the spectrum point of view, and actually there are different kind of there are different kind of spectrum, and inside the spectrum, different kinds of spectral shapes, there are different components. Some of them are extending to higher energy, and also the emission at high energy seems to last longer. So we have a chance also for detection with the Cherenkov telescopes. MAGIC is trying hard, more or less following 10 per year, which is the maximum we can follow. We do not skip any. And we have an improved algorithm since 2013, so we're trying to do our best now. And we are trying still to improve the algorithm, actually the energy range of the detection of the detector, more or less, to see if we have more and more chances. But up to now, due to several problems, we did not find any GRBs. But we are still looking, and soon CTA will come, and so this will help us even more. That was it. Thank you.
Thank you very much, Elena, for your nice talk. Questions?
Have you seen any repeated gamma ray burst? I mean, in the same location?
No.
No. Have you looked for that?
No, but I haven't heard. It would be big news. It's not. Normally, yeah, the sky is too big. No, no. Also because, as I said, some of them really show a connection with supernova, and then when you see the supernova, that's it. And some of them has so poor location, actually, that I mean, within 3 degrees, maybe there is another one, but how do you associate it with it?
How do you determine the redshift of a GRB, in particular of these very high redshift GRBs?
Well, the very high redshift.
You mentioned 9.
Yeah, yes. I forgot. Normally, the ones closer are done with the optical part, but the ones further. No, sorry, I forgot how they do measure. Peppa? Could be. Yeah. No, no, I think. No, it's not, absolutely not from the gamma rays. Maybe in radio. Radio. Hmm. No. No, I think the maximum was around 6. Yeah. No, but this is for sure not done in gamma. It's not measured in gamma. The redshift is never measured in gamma. Maybe from the X-ray spectrum, the lines.
Okay. Yeah. So one more question regarding the redshift. I know, well, one of the big issues is to get the redshift, and it is so important in the very high energy regime because of the EBL absorption, etc. And still, there are many GRBs for which you don't have that information. So I know Sylvain Guirec was working on this method of feeding 3 components to the spectrum and then use GRB as a standard candles, because apparently you could derive from the spectrum, from the gamma ray spectrum, the redshift. I know this method is highly debated in the field, so what is your feeling or what is your opinion about this model, and can we in the future, once it is more tested, use it for CTA, etc.?
So I think there has been other models before that try this. This is this Amati relation. I don't know if you heard of it. It's been sent out several times. several years ago. Finally, this amateur relation was a product of selections, basically, because your instrument can prefers this kind of GRBs, and then the threshold for flux and the threshold for energy. At the end, it basically takes your energy and flux space, and it reduces it to sort of a line. And therefore, from that, it came the line. This other one of Sylvain Guillec, I am not so convinced, because of course, it implies that each GRB has 3 components, spectral component, just to let you know, in the spectrum. And these 3 components are more or less always present, and one of them, if I remember well, gives you tracks more or less the standard candle. What I can see is that I saw it blindly applied once, and for this GRB that has been applied to, it predicted a ratio of 10 on a LUT detected GRB, which is okay. It could be. Nothing says no, but starts to be hard. So I've seen it from him tried out, of course. So in his selected sample, it works. What normally makes it real to me is that you take something, you randomly run this thing, and gets redshift, and that this redshift is actually compatible with what makes sense and you expect.
Thank you. Just one more question, because even if you are biased, I mean, probably if you know your bias, maybe you can use the method in the terms that your method might work for a given sample of GRBs, in the sense that you can select them for the, using the flags or the spectral index or whatever. So at least you will have an instrument or a way to have a handle of the redshift, even for a subsample of the LUT detected GRBs. Well, just do you think?
No, this doesn't work for the amateur relation. It's just because the more you expand basically your threshold, your flux threshold. So the more the less bias you have, the more it becomes a blob, and not any longer a line. So, welcome. But I mean, let's see how it goes. I'm not saying the final word. This is my opinion. Could be that it works out. The amateur relations stayed up for years and years.
I have one very fast. Now in this epoch of multi-messenger astronomy and stuff like that, it's becoming very popular to search for popular, of course, they are not very easy to catch events, but it's becoming very popular to search for neutrinos in correspondence to gamma ray bars. So, of course, with MAGIC, I have no idea, because we didn't detect gamma ray bars, we didn't detect neutrinos, so I don't know. But in general, do you think it's possible to have something like that?
Yes, I mean, there are several models, mostly not the models that I showed you, because these ones are so-called leptonic models, but the hadronic models for the emission, of course, predict neutrino contemporaneous to gamma. Up to now, you know, IceCube has run quite extensive search for GRBs in coincidence with neutrinos, and they found nothing. They just put upper limits on the models. So what they did, they put upper limits on the flux of neutrinos, that it goes into the amount of hadrons that there must be in the system, in the jet, in the outflow jet. and it doesn't really constrain much because nobody knows what is the content of the jet. As we don't know the progenitor, we don't know the environment, we have no idea and no clue of what is inside the jet. So what you can do is, of course, place limits on what is the amount of baryons with respect to leptons. After the IceCube people put the limit, all the models have been reviewed to a lower This is the usual game, no? When you know nothing, you put a limit and all the models are reviewed. It could be because, as I said, there is not a clear picture that the jet outflow is actually mostly leptonic and that we get emission from leptons. It could be that what is emitting are actually hadrons, or at least a part is a hadron, and then we can get a neutrino flux. But maybe this part is very, very small. I mean, surely hadrons are very efficient in the emission, but they are not very efficient to accelerate, while leptons are much more efficient to accelerate and give you, still give you high energy emission that you can see. So if hadrons produce actually part of what you see, they might be very small. It might be a very small part.
Thank you so much, Elena. We don't want to stress you with too many questions.
No, ask me more if you want.
No, maybe in front of a coffee. Okay, thank you so much then.
Thank you.